Right. They're mostly empty space.
Yeah, fundamentally empty.
So what if you could just, like, take away all that emptiness, get rid of all the electrons buzzing around? What are you actually left with?
That's a great way to put it. And it really sets the stage for what we're diving into today, how an atom turns into just its bare nucleus.
Exactly. You might have heard the word ionized thrown around, or maybe just wondered about, well, really extreme matter.
Right.
So today we're really digging into that. We'll start with the regular atom, the neutral one we all know.
A baseline, yeah.
Then look at the energy needed to strip off those electrons and what this bare nucleus thing actually is, its properties, where you find them.
From stars to labs, exactly.
And we're basing this whole chat on that material you shared, atomic ionization, from atom to bare nucleus. So let's jump in.
Okay, so starting point, the neutral atom. You've got the nucleus in the middle, protons, neutrons.
Positive protons, neutral neutrons, got it.
And around that, this cloud of negative electrons. And crucially, in a neutral atom, the number of electrons matches the number of protons. So, zero charge overall.
Right, it's balanced. And I always picture it like planets orbiting, but it's not quite like that, is it? It's more about energy levels or orbitals.
Exactly. Think energy levels. And these electrons, they're not just floating free, they're bound there.
By the electromagnetic force holding them in. So you need energy to pull one off. That's the binding energy.
That's precisely it. Each electron has a specific binding energy holding it. To ionize the atom, to remove an electron, you need to give it at least that much energy.
Okay, and the material mentioned using light, photoionization.
Photoionization is a key way. A photon, a little packet of light energy, hits the atom.
But it has to be the right kind of light of the right frequency, it said.
Yes, because the energy of that photon depends directly on its frequency. Remember E. Higher frequency light, like UV or X-rays, carries more energy per photon than, say, visible light.
Okay. So if the photon's energy is high enough...
If it meets or exceeds the electron's binding energy, boom, the electron gets kicked out.
And the atom becomes an ion, positive charge now.
Right, it's lost a negative charge.
Okay, so that's one electron, but stripping all of them, that sounds intense. It's not just using a brighter light, is it?
Oh, definitely not. It gets harder and harder with each electron you remove. That's sequential ionization.
Why, though? Why does it get harder?
Well, two main reasons. First, once you remove an electron, the remaining electrons feel a stronger effective pull from the positive nucleus. There's less negative charge shielding them.
Less shielding. Okay.
And second, there's less electron repulsion pushing them apart. So the ones that are left are held even more tightly.
Okay. So the positive nucleus has a tighter grip on the fewer negative electrons remaining. Makes sense. So more energy for the second electron than the first?
Much more. And even more for the third, and so on. The material really emphasizes this, especially for heavy atoms. Think uranium, 92 electrons.
92, wow.
Getting rid of all of those, you need progressively higher energy. We're talking maybe UV for the outer ones, but hard X-rays, maybe even gamma rays for those innermost electrons, or other really energetic processes.
Okay, so let's say we manage it. We pump in all that incredible energy. What are we actually left with? Describe this bare nucleus.
Well, you're left with just the nucleus. Protons and neutrons, assuming the original atom, the isotope, had neutrons.
And it's got a positive charge, right? Because all the electrons are gone.
Exactly. A net positive charge equal to the number of protons.
So for hydrogen, just one proton, it becomes a bare proton.
Yep.
Helium, 2 protons, 2 neutrons. That's He. An alpha particle.
That's the one. And uranium, a massive positive charge.
And you mentioned isotope before. That just means same element, different number of neutrons.
Correct. The neutron count affects the isotope, but the charge comes from the protons.
And the size. You said the nucleus is tiny compared to the whole atom?
Oh, incredibly tiny. The electron cloud defines the atom size. The nucleus is something like 100,000 times smaller in diameter.
Whoa, 100,000 times. It's almost impossible to visualize. So you strip away the cloud, and you're left with this tiny, super dense, positively charged speck.
That's the picture. This bare nucleus.
So what's it like? Does it behave like the original atom at all, chemically speaking?
Chemically, not really. Let's talk stability first. Its nuclear stability, whether it's radioactive or not, depends on the proton-neutron mix, just like any nucleus. Losing electrons doesn't change that fundamental nuclear property.
Okay, so a stable nucleus stays stable, a radioactive one stays radioactive. Got it. But chemistry?
Chemistry is all about electrons. Sharing them, transferring them, forming bonds, making molecules.
The electron cloud stuff.
Exactly. A bare nucleus has no electrons. So
Yeah.
it can't do any of that. It effectively has no chemical properties in the traditional sense.
Right. No bonding, no reactions like we usually think of them. So how does it interact with stuff?
Its main thing is that strong positive charge, now completely unshielded. It has a huge attraction for electrons.
So if it bumps into electrons.
It'll grab them.
Yeah.
It readily captures electrons, trying to become neutral or at least less charged again. And it's moving fast, with high energy.
Yeah.
It can rip electrons off other atoms it passes through. It causes ionization itself.
Ah, so it's not just being ionized, it causes ionization too, like a tiny charged wrecking ball.
Sort of, yeah. It interacts very strongly with matter because of that charge.
Okay, let's recap the key features then.
Yeah.
High charge density, obviously.
Very high.
Yeah.
All that charge in a tiny space.
An extreme electric field around it. No electron shells.
Not at all.
And this really strong pull, this affinity for electrons. Anything else? Relativistic effects, maybe?
Yeah, the source mentions that for very heavy nuclei, or ones moving incredibly fast, close to light speed, you have to start thinking about Einstein's relativity. Their mass increases, time dilation effects. It gets weird.
Okay, that's pretty mind-bending. So these things sound super exotic. Where do we actually find them? Not just floating around here, I assume.
No, definitely not under normal Earth conditions.
Yeah.
But the universe is full of extreme places. Think about the core of a star.
Like our sun.
Exactly. Temperatures are millions, even billions of degrees. It's so hot, atoms are just completely torn apart. You get a plasma.
Plasma. So that's basically bare nuclei and free electrons all mixed up.
Pretty much. The sun's core is mostly bare protons, hydrogen nuclei, and alpha particles helium nuclei. That's what's fusing together.
Wow. So the fuel for stars is bare nuclei. That kind of reframes everything.
It does, doesn't it? And think about even more violent places. Accretion disks around black holes or neutron stars.
Intense gravity, super high temperatures.
Perfect conditions for stripping atoms bare. Same goes for supernova remnants, the clouds left after stars explode. The shock waves and heat do the job.
So cosmic violence creates them. But you said labs, too. How do we make them here?
Particle accelerators are key. We accelerate ions, atoms that have already lost some electrons, to really high speeds.
Okay.
Then we shoot them through a thin foil called a stripper foil or a gas. The collisions are so energetic they knock off more electrons, sometimes all of them.
Creating beams of bare nuclei.
Exactly. Beams of UO, for example. We use these for research nuclear physics, studying materials.
And you mentioned medicine.
Yes, hadron therapy. Using beams of protons or heavier ions, sometimes bare nuclei, to very precisely target cancer tumors, delivering energy right where it's needed.
That's amazing. Using these extreme particles for healing. What about lasers? The material mentioned high-intensity lasers, too.
Right. If you focus an incredibly powerful laser onto a tiny spot, you create a mini plasma. Super hot, super dense for a fraction of a second.
And that strips electrons, too.
It can create highly charged ions, yeah, potentially even bare nuclei in some cases. It's another way to reach extreme conditions. And don't forget cosmic rays.
Ah, the particles hitting Earth from space.
Some of the highest energy cosmic rays are actually bare nuclei iron. For instance, accelerated by who knows what powerful events out in the galaxy.
It always comes back to energy, doesn't it? The energy to strip them, the energy they have when they're created in these violent events.
Absolutely. It takes a huge amount of energy to remove every single electron, the sum of all those increasing ionization energies.
That light of the right frequency idea?
Mm-hmm.
You need more and more energetic photons.
You do. Maybe UV for the easy outer ones, but you quickly get into X-rays, even gamma rays for the inner shells of heavy elements. Though realistically for complete stripping of something heavy.
It's more likely collisions in a plasma or accelerator.
That's generally how it happens, yes. Collisional stripping is more efficient for removing those very tightly bound inner electrons than trying to do it photon by photon.
Okay, so let's try and wrap this journey up. We start with a normal, neutral atom, nucleus plus electron cloud.
Balanced charge, mostly empty space.
We apply energy, often a lot of energy, sequentially removing electrons against an ever-increasing pull.
Harder and harder each time.
Until only the tiny, super dense, positively charged nucleus remains.
We're spare.
It loses its chemical identity but gains this intense charge and electron hunger.
Interacting strongly with matter in a whole new way.
And we find these things in the most extreme places: star cores, black hole disks, supernovae, accelerator beams.
Environments defined by immense energy.
So the big takeaway seems to be, strip away the electrons, and you reveal this fundamental core, the nucleus, which is just radically different from the atom we started with.
Completely different character. It highlights how much of an atom's everyday behavior is down to its electrons.
And it leaves us with a pretty interesting thought, doesn't it? You said most of the visible universe is plasma?
Bare nuclei and free electrons,
Yeah.
By mass and volume, it dominates.
So maybe that's the normal state of matter, and our familiar neutral atoms here on Earth are actually the exotic exception.
It certainly shifts your perspective, doesn't it? What we consider normal might just be a quirk of our relatively cool, calm corner of the cosmos.
Definitely something to chew on. Thinking about those bare nuclei out there, the energies involved, it really opens up whole areas of astrophysics, nuclear physics, fascinating stuff.